All right. Welcome to another stream building an Atari 2600, um, Atari 2600 emulator in Rust. Um, Last time we left off after fighting with some integer conversion stuff, we ended up implementing branching. So let me go ahead and see. Do I have it? No, I don't have it open. So let's go to that file, main.rs, where everything lives right now, and we have implemented the flag z for whether, which is the zero flag, and we implemented branch not equals. Still to do, now that we have flags and now that we have branching, there's a ton of instructions to implement, and I'll get to some of those, but I might not do all of those on stream because a lot of them are going to be super repetitive. But I wanted to do some of the more interesting challenges that we're going to come across. Um, so I think let me think. The next thing we're going to do today, we're going to go over a little bit of stuff that I hand waved about integer conversion here, just to explain that really explicitly. If you know two's complement, and if you know your hexadecimal and binary stuff better than me, this will probably be pretty um, fundamental, pretty basic, and maybe a little bit wrong. But it's definitely something worth reviewing. And then I think we've gotten to the point where it'd be really nice to see what is happening to our memory, our program, and our registers and pointers and stuff as we execute the program, rather than simply, let me see, map E colon W cargo run with a carriage return, rather than I think I got rid of all of our debug logging, but rather than just debug logging out the whole structure every time, that is getting pretty annoying. So I think for now we are going to pull in cross term and do a little bit of pretty ugly sort of terminal printing stuff as the program executes. This is not yet going to have anything to do with graphics. We haven't gotten to that yet. That's a whole another story. Actually, I can show you exactly in the program that I'm testing this against where we've gotten, which is tic-tac-toe source. This is a home-rolled version of tic-tac-toe that I created a few years ago. Um, let me see something real quick. Okay, I'm not dropping any frames, which is good. All right. Tic-tac-toe.dasm is the one that we're using. Oops, sorry. And we, a bunch of setup here. And this is kind of where we've gotten through in the execution. Um, we have loaded X. We have loaded A. We've stored the accumulator, or yeah, stored accumulator into memory at 0 with an offset of x, and we are incrementing x. Oops. And then we are and then we are jumping back. This is a simple loop in assembly, so jumping back to the clear, storing it, and then we continue to increment x until it rolls over to 256, which will be 0. So then we're loading this immediate value, um, which is 256, and then we were storing that as the stack pointer. So this is where we are stuck, and then we'll eventually get to. I think we'll be able to do all of this stuff. Yeah, we'll see what this looks like. I think there's going to be some absolute positioning stuff we need to do here. So, um, but I will say that that's one line. This we need to be able to set the stack pointer. Yeah, it's setting the stack pointer to 256, which is the end of RAM, and the stack grows downwards, which is pretty standard stuff, into RAM. So if you thought that 256 bytes was a limited amount of RAM, it's shared with the stack pointer. For this reason, I find it very, very. This reason and the fact that function calls are super expensive in compared to other instructions, um, that you'll very rarely see functions, although they do exist in 6502 assembly. So honestly, the stack ends up being not super useful. I'm probably missing some use cases, but not how you would normally think about it. Um, but it is sort of customary to set it up. And even though I'm not sure anything would break. All right, so let's take a quick second to talk about what I was struggling with last stream that I sort of glossed over. The so the branching. So BNE. There's a bunch of other branching instructions. Let's see if I can pull those up real quick. BNE. Right. Um, all of these they are relative. So basically, you branch with a displacement. The assembler usually does that with a label. That is definitely the easier way to do it, rather than trying to count back bytes and stuff like that. However, this is in the case of our loop, we were going back 5, and I was pulling this off originally as an unsigned integer 8, and then trying to figure out how to add it. Um, the important thing to note here is um, the program counter is 16 bits, um, and we needed basically for. I'm going to see if I can do this real quick. So the relative address was, let's see, it would be 255 minus 5, so it would be, this could be wrong, is 250, which in hex looks like, we'll go with how the assembly works, which would be F, then F is -1, G, E, F, G. Okay, I can do this. Count it, going backwards from F. E, D, so -3, C, -4, and B is -5, right? So if I simply took this as a U16, what would happen is that we would get the more significant bytes being 0, and adding that to, let's see, adding that to the program counter, which is at 1,000 and something. It doesn't really matter exactly this. Actually gets us skips us way ahead um, in the execution of the program. And what we need to do is treat this as an I8. Um, so, and then I think the conversion to a U16 makes this look like FF, FB, which when you add it to the program counter with a wrapping add, actually I'm going to try something real quick before we move on. Makes this wherever, if it was at 1,000 and we'll go with 6, when added it would roll over the 16 bits that we have, and it would come back to 1,000. 1, 1. Right. And that is because of how negative numbers are stored in binary. Um, it's called 2's complement. It can trip you up, but it's pretty simple. If you have a byte, in this case representing a negative number, the most significant, or is it least significant? I don't remember. Byte here, if it's a 1, then it's a negative number. And in fact, what is this? 1, 2, 3, 4. Space 1, 2, 3, 4. Right. This is, while this might seem like it would be a small negative number, this is in fact a very large negative number in 2's complement. So the largest one would be, or the smallest one would be, and this is -1. The point being is that you don't really have to know whether it's negative or not. You don't have to do a test on this first bit or anything, or do anything fancy to add -1 to another number. In fact, if I say I have the number 1 in binary, this is the number 1. And I add 1111 to it, you can see that it'll overflow. And we can just kind of do that arithmetic. It's similar to like what you might expect. So we do 1 plus 1 is 0, and you carry the 1 over, and 1 plus 1 is 0. Carry the 1. Right. Carry the 1. Carry the 1. And then we have 0. I think this is how it works. I might be fuzzy on some of the details, but that's the basic idea. Maybe we could do a more interesting version with the number 2. Get that. So this is number 2. Adding those together, we would expect to get the number 1 out. And we can see how that would work by doing this math. Right, here we have 1. Here we're adding 1 and 1. We have a 0. We're carrying the 1. And doing the same exact thing that we did last time. And just to get it super in my head as well as yours, we'll do it with an odd number and see what happens there. 3. I have one viewer. If you're joining us, I'm explaining some 2's complement stuff, how negative numbers are represented as in bytes, because I struggled a little bit with them last time. And I am just sort of like clarifying since I sort of hand waved it once I got this working last time around. Then we're going to move on to being able to view registers and stuff as they change. Since implementing a bunch of these instructions for the Atari 2600 are going to be repetitive, I'm going to do those off stream, but I really want to be able to see the memory addresses and registers as they get updated. I think that'll be a little fun thing I'll pull in cross-term and just have it show a little bit of data. Cool. What was I talking about? Oh yeah, I was going to demonstrate adding -1 in 2's complement and adding the number 3 in binary, and then I'll just and then I will move on. So right, so This is where I think I might have had something wrong. So what happens if we add 3? So that's 2, 3. So 1 and 1 is 0. 1 and 1. Uh, carry the 1. So that's 1, 1, and 1. Right, that makes sense. Carry the 1, which is 1 and 1, is 0. And then, yeah, sorry, let me go back there. So 1 plus 1 is 0. We carry the 1 over here. We have 3 ones to add together, which is 1, 1. So we'll put 1 down and carry the 1. And then as we carry the 1 here, we will end up with 0 all along the way, which gives us 2, right? So 2's complement is like a simple but ingenious way to like make arithmetic with binary numbers extremely simple, and not having to worry about doing conversions and checking signs and stuff like that. You can just treat them the same and add them together, and everything just works. All right. So we're going to use a library called crossterm. So let me open up my cargo.toml to visualize all this stuff. And I've worked with crossterm, but it's been a while, so I think, let's see, I have some information about it here. So I'm actually going to open another project where I've used it and copy from there. So look at that cargo toml. The version's probably outdated, so we'll probably want. I don't know that I want an event stream, so I can probably just do whatever the most recent version of crossterm is, which is going to be 23.1. So equals 0.23.1. All right, and while I'm doing that, I'm going to go look at this previous project. It's already in terminal, and then I think it's in lib here. Actually, maybe there's something in main too that I need to steal. Crossterm. No, it must all be in lib. So. All right, so in crossterm U has some really nice. Okay, yeah, you can just pull standard out. Do I need to standard out? Okay. So setting it up, enter alternate screen. Okay, so then there's enabling raw mode, setting the size to the terminal size, and then I think there's like something you have to do afterwards. Leave alternate screen. So you just want to like clean up after yourself. It's implementing drop for terminal, but we'll just do it kind of manually. So let's go to main.rs and we're going to import. We'll probably want Okay, we'll probably want a lot of this stuff. We're going to need a little bit more out of cross term too. Probably just color. I don't know that we need event. I think we're just going to quit automatically when the execution is complete. So this is telling us that like a lot of this stuff is doesn't exist. So event stream. Yes, I don't have events, so I'm going to get rid of like all of that. Let's see. I got execute, queue, style, self print, terminal, self clear type. Okay, so that should remove the whole use item. You're not using it. Okay, so then we're gonna look at the setup here. We'll just go ahead and do that at the beginning of our program. We might just make a quick function just to keep it out of sort of the main execution of our program since we're doing everything in line right now. So we'll just do function setup. This is pretty imperative stuff, so I don't like even think I need to return anything or keep anything around. I think I just send essentially global commands and that it works that way. So setup. Okay, and then I'll just copy a bunch of this stuff. Yep. That's not in the function declaration, it's in the body. Okay, yeah. It wants a result. I can actually just make it a cross term. Do I have a result here? Yeah, I'll just pull this over. Just a little type definition for result. We'll need error. I think that's a fine error to bring in. Okay. So terminal will return the result of unit. We basically just want it not to panic here. And I need standard out. Pull that. Then I don't need size. It's going to handle that on its own. So we'll just do setup terminal expect terminal be set up. And before we leave, we're just going to say tear down terminal. Then we will pull over the terminal teardown stuff that we have, which is not too much. Subterminals define. This is tear down terminal. Map this into a unit for now. Since this is sort of temporary code, I'm not too worried about it. Yeah, okay, so it wants that. What else is it saying? Wrap expression in okay. I shouldn't have to do that. Incompatible types. Jeez. Actually, I don't have to do this. That's right. Okay. So I can just return it. Okay. That should all work. What is it not like? Unreachable statement. What is happening? Oh, right, because it's panicking. So instead of panicking, we'll just break. So we'll. So yeah, we won't do that, but we will print line, right? That we're not handling that instruction, and then we will break the loop, and then we will be able to tear down our terminal. That's something closer to what we're going to want to do anyway. We will use. I think right now we can just see if it is working at all. Actually, for now, because it's going to take over the terminal, I'm going to do it in here. So it should be very fast, but it should probably flash the screen and then go away. It did not. So I don't think I'm actually clearing the screen. So it probably didn't even show that. So where am I doing that? Probably where I'm using clear type. So I'm going to queue up some stuff. Style, reset color, cursor, hide, move 211. Okay. So after I set up the terminal, I'm going to keep all of this in methods essentially. So I'm going to do. So before everything else, I'm going to clear screen. We'll keep it named terminal. Expect. Couldn't clear terminal. Clear. after I write this little bit of code, I'm just gonna kind of explain what everything does. So pull this queue over. We need the standard outs, which we're using everywhere else. This needs to return a result. What else doesn't it like? Yes. I need to return OK. All right. Okay, so here we are. This it's a lot going on. Actually, let's just run it and make sure that it's doing something reasonable. Might be going so fast that it can't even do anything. So let's do a sleep. Let me make sure that I know how sleep works in Rust. It's been a while. I need sleep from standard thread sleep. And probably sleep milliseconds. Okay, so we'll do a couple thousand just to make sure that we can see what's going on. What doesn't it like? You're right. Okay, that's what I was seeing. I didn't realize it was deprecated. We'll do time duration from millis. Yeah. Time duration from millis to 1,000. No big deal. Did I spell duration wrong? Failed to resolve duration. Standard time. I'll get it one day. Okay. Cool. Now we can see the terminal being taken over, and this debug print is being is at the bottom of the thing. For fun, we can do a different color and make sure that it's not clear terminal colors. Let me look how it did colors here. So we'll set the background color. Let's take a look at the docs for set background color. Let's see, color for more info. Set colors can also be used both the foreground. online documentation for cross-term color. Set background color. So we'll do. Oh, okay. So it's just a color. One of those colors. Color. Magenta. It's probably need to do the reset color. Might be that resets. Can I change that? Oh, I bet I know what's going on. Let's see. Tear down terminal. Set background color clear. Clear type all. Okay, well, I'm not going to worry too much about that. I think I'm misunderstanding exactly how that works. But instead, we're going to start drawing stuff. So after each instruction is yeah, we're sleeping. I don't think we're going to want to sleep for 2 seconds between each instruction, but we will want enough time to see things as they happen. So for right now, we'll just go for 500 milliseconds, a half a second between each step so we can see them updating as we go. And let's see, we're going to draw before that. So we're just going to say draw terminal. We're going to pass in a reference to our chip. I think that's already, no, it's mutable, so we're just going to pass in a reference. And we're going to do, we're probably going to need to expect. Couldn't draw terminal. And we're actually going to need to do this inside our loop, and we're actually going to need to sleep as well afterwards. Otherwise, it'll just loop very fast. And we need to implement draw terminal, so we'll do that. Probably pull this out into utility module at some point soon, but for now we can just leave it here while we're working on it. Draw terminal. We're going to do chip is a reference to chip nmos reference to our chip. Don't think it's going to make sense for us to All right, I need to go take a quick break. I'll be back in a minute. All right, we're back. We were in the middle of setting up our terminal and um, I was just trying to think of something. Anyway, setting up our terminal so we could look and see what is happening with the Atari 2600 as we do operations. So I think we're pretty much set up to do that. We're going to do a draw terminal. I just need to remember exactly how this works. I think it's pretty straightforward. You set background characters and you print characters. Now the question is, print. What does that take? That doesn't. I don't think I've got stuff installed there, so it's not liking it. Resolved macro clear terminal. What has happened to my? Okay, that's here. Let me declare Vim bankruptcy. Start over again. Oh, I messed some stuff up here. How did I do this? I nuked my main function somehow. Should main. Cool. Okay, yep. Draw terminal doesn't turn the right thing. Let's see, draw. Let's return. A result. We don't really care about any data involved in that. And then we're going to take a look at my old project again. Source lib. It should be somewhere that we can just kind of steal some stuff. All right. So we're just gonna. It's not gonna be pretty. We're just gonna do this in a kind of dumb way, but hopefully we'll get some useful debugging sort of information at our fingertips as we go through. Okay. So we're gonna do Q. I did promise that I would explain what all this does. All right, okay, I will start there. So, um, so CrossTerm is a like cross-platform library that tries to abstract away a lot of the sort of intimate details of terminals on different platforms. Specifically, I do think it supports Windows, which is kind of the odd man out as far as terminals go. And so, like a lot of the things that it's not perfect. Like it can't perfectly abstract them, but it does like allow you to enter the alternate screen, which is the sort of way it takes over the entire screen. Enables raw mode. Enabling raw mode is like a pretty complicated and not uniform operation, so it abstracts that away. But that's like turning off cursor echo, turning off just a bunch of stuff, and then it allows you to execute some stuff. I'm really unsure what the difference between execute and queue is. I think execute is like it says like do this now, and queue says like store up actions and flush them. So in the case of setting up and tearing down, we want things to happen as like right now. So resetting resets all the colors. So if you had something weird, uh, if you had something set up like foregrounds, background colors, they won't bleed out into the terminal. I'm sure everybody has seen programs that aren't very good about cleaning up after themselves. And in fact, if we had a panic somewhere in our code, which we shouldn't worry about that right now, but may happen eventually, we would not be cleaning stuff up very well. So we might need to implement like drop, which is what I did for my other from my other project. And then it leaves the alternate screen. It shows the cursor again, um, and then clearing the terminal just uh, is something you kind of do every. Actually, I may need to do that more often. Yeah, actually, I'll need to do that probably every loop for now. Might be a little janky. There will be some flicker or something like that. Solving that is a sort of different problem. Um, cool. Um, yeah, so it's resetting colors. It's clearing. It's hiding the cursor again. It's move. I'm not sure that that's actually necessary. Let's leave it for now. Okay. Um, and then it's moving the cursor back to 1, 1, leaving it in sort of a known state. And so to draw, basically, the way that these macros work is that there are a bunch of commands. I'll show you here. Move to, set foreground color, all that stuff. These are enums essentially. So you can declaratively like sort of say, here's what I would like to do here, and then so it queues up these commands and it knows how to execute on each of them. Yeah, so I think that's about it. We'll need to grab standard out from one of these other ones, and then the first argument to queue is standard out or whatever buffer you're writing to. Doesn't like that, but that's fine. We're gonna cursor. So we're just gonna kind of do this like manually, or this will be a pretty gnarly function. There'll be some loops in here and stuff like this. But we'll actually just start where it is. Maybe we'll indent. Yeah, let's indent a little bit, like 5 characters. Move to alignment to column and row. Yeah, I think that's good. We're gonna start first with all the, and we're just gonna do it row wise, rather than trying to figure out how to split things into columns or anything like that. We're gonna do it row wise. We're gonna start with the chip. We're gonna or the like stuff on the chip, like the registers and the like stack pointer when we get to it, and the program counter and all of that stuff. Then we're gonna under that we're gonna sorry, just thinking ahead. Under that we're gonna print out the memory, which is only 256 bytes, and I misspoke earlier. It's 128 bytes of RAM. The other bits of memory are memory mapped devices. So the TV interface and all that stuff are in the first 128 bytes. So the story is even worse. It's 128 bytes of RAM that you share with a stack pointer. Fun stuff. So we're gonna actually we'll just maybe, since we're on the same thing, we're gonna move right. Move 5. Then we're going to queue up a print. We'll call this 6502. That's the name of the chip. Right, and we'll need to get rid of that somehow. We'll need to hit OK. Okay, and we actually should be able to run it and see. Actually, I'm curious what it's going to look like if we run it in the terminal. So we'll need map. That's good. It's not great. Actually, I think that was fine. I think I just forgot to set some stuff up, right? So, I think we're gonna set that up first. We're gonna style set foreground color. Okay. May need to. I may be missing a flush here. Yeah. I should have standard out here. Why is flush not available here? Did it change or something? Let's see what the cross term stuff says about it. Flush. This is cross term. You. Complete control over when to flush. When right and flush. Okay. Centered out Q. Centered out flush. Okay, so I must be missing something here. Um, Samples macro. Macros. Standard out dot flush. Execute key style terminal result. So why is this not? Do I need to pull in right too? I probably need to pull in right. Yeah. I think that right is what implements flush and all those other things for standard out. Yeah. Okay. So now when I run this, take over the screen. Yep. Okay, and there it's writing nmos. Yeah. Okay. It's on a different column than I would have expected. Let's see what that looks like in the actual terminal. Ooh, I've gotten a good spot there. Got to restart Alacrity. That's super fun. Sorry for the delay while I get this all set up. At least that is there. So if I Control plus, should get us close to. There we go. Okay, that's sort of close enough. All right. Where was I? All right. Um. Oh yeah, I was trying to go background my Vim uh, process so that I could run cargo here. All right, so it does appear to be that it's offset by 1 by default. So maybe 1 1 is not the thing for the clear, which is interesting. If I move to 0 0. Yeah, that seems to work. It also seems to be colored. No, I think the difference in color was running here versus cause the terminal in Vim is different than the one in. All right, so I think I've stolen everything I need from my former project to make this work. I think for right now I'm just going to try and get everything printed out, and then I'm going to see if I can do something fancy about like checking the whatever changed in the last iteration and highlighting that somehow. Not entirely sure how I'm going to do that right now. But yeah, and so then we're going to just move cursor, move down by 1, and sounds like my child is awake. I'm going to have to go ahead and end this stream for a minute. I might be right back. 1 second. And she's back asleep. Yeah, I'm on wake up duty, so I'm going to see if I can get a little more done before she's awake from her nap. Cool. Cursor move down. Cursor. Oh, let's do it. Move to next line. Command that moves the terminal cursor down, moves it to the first column. That's actually what I want. Move to next line. Doesn't it like about that? The trait bound. takes a number. Oh wow, that's okay. She is awake. I'm gonna have to stop for now. I, I'll be right, or I'll be back a little later.